Hello everyone, welcome to the final lecture of week 6. So we have been discussing about pre-training in this week, and in this particular lecture we'll discuss more about pre-training, different interesting aspects. So we will focus on how do you pre-train for specific domains. So if I have a data from scientific domain, financial domain, how do you pre-train? What about multilingual pre-training? How do I pre-train it for various languages? And I'll also talk about uptraining, and this has some connection to the last lecture that we took for week 5. So let's talk about domain specific pre-training, right? So typically when we use pre-trained data, pre-trained models, so we are talking about general domain. So we take corpus such as news and Wikipedia and train large models on this general knowledge. But now suppose I want to say I have problems in the scientific domain, financial domain, biomedical domain. So how do I extend these models? And you would see, and in all these domains you may have a lot of data, right? So you can even pre-train on this data, but can you also make use of whatever you have pre-trained in the previous general domain like BERT? So for example, in scientific domain you have SciBERT, in financial domain you have FinBERT. So they're all variants across domains. You have BioBERT, and so on. You have different variants in different domains. So how do you decide whether I will start from BERT checkpoint and continue pre-training, or I'll pre-train from scratch? So I'll focus on SciBERT to give some idea how did they decide and did their experiments. So SciBERT is a pre-trained model based on BERT. So they train it on a large scientific text. So what is the recipe? So first of all, what I need to decide, I can use BERT framework as it is, right? The BERT framework is very easy. The code is available, I can use that. But the question is, do I train it from scratch on this domain data, or I already use the BERT pre-training checkpoint and continue from that? And this is what is called continual pre-training, CPT, continual pre-training, right? So whether I do scratch pre-training from scratch or continual pre-training, right? And one may say option 2 looks better, because there I can already make use of the knowledge that this has learned about general domain, and why would I lose that knowledge, right? Start from that knowledge and continue telling it about scientific domain, and that should have been a better choice, right? But this is not always that simple an answer, right? The answer lies in something about the vocabulary, right? So when you say I am training a model, it also has a vocabulary, right? So BERT has a vocabulary. So BERT uses word piece, and this is like BPE, so it will use the most frequently used words or subword units. And let's say this is the base vocab for BERT, right? Some 30K plus. Now, the authors of SciBERT, they also tried to compute the vocabulary using the same process for their scientific domain that they had, the data that they had. And this is what they called SciVocab. First of all, they wanted to see, is there an overlap, significant overlap between SciVocab and base vocab? And they found this is very low, just 42% overlap. That means it has 58% new words that base vocab did not have. And you would obviously like to have these tokens included in your vocabulary, right? Because otherwise what would happen, these tokens will be broken up into subwords and would lose the significance, right? So you typically want in a new domain that the tokens should be retained as much as possible. So there is a variation, right? So now I am already using a base vocab in BERT model. If I want to do continual pre-training, I have to continue using the same vocabulary. I cannot replace the new vocabulary. But if I want to use SciVocab, then I have to pre-train from scratch, right? So these are the two choices. So if you want to continue pre-training on BERT, I have to use the original vocabulary, and if I want to use new vocabulary, I have to pre-train from scratch, right? So in their experiments, what they found, if they do from scratch with SciVocab, they get slightly better results, right, over continual pre-training with base vocabulary. But what the authors themselves said is that given the vocabularies were very, very disjoint, and the kind of improvements they were seeing over birthways, right? So they found improvement with both the models. So they said in-domain vocabulary is helpful, but the main benefit comes from the scientific corpus pre-training. So this is very, very clear. So it's if you can pre-train on your own corpus, on your own domain, it's always beneficial. Now whether you want to use your domain vocabulary, then you have to pre-train from scratch, and that will take more time. So this will take more time. But if you want to continue from pre-training from general domain, that will require less time, right? But you may have slightly less gain because you are not using domain vocabulary. So there is always a trade-off between what exactly to use. Now we will come back to this point, like, can I not extend the vocabulary, right? We will talk about that briefly also in this lecture. But there is a side effect of continued pre-training that also one must be aware of. One has to be aware of. So what is that? See what is happening. I have a BERT model that is pre-trained on general data. But now let's say I took a very specific domain and continued pre-training from the checkpoints, right? So what can happen, because I have pre-trained it for a new domain for a long time, it forgets the knowledge about the general domain. That's a very common phenomena known as catastrophic forgetting. Like here what you are seeing, this was the Roberta base model and applied on glue benchmark. And now in this paper what they did, they used e-manuals. They trained Roberta for e-manuals domain, and then they again tried to test the performance on the same glue benchmark, and they found there was a huge drop in performance of the Roberta model, right? So you see catastrophic forgetting, and there are of course remedies for that, but this is a very commonly known problem. Like one common remedy is that while you are pre-training on new domain, you keep on mixing some data from the general domain, so that does not forget general domain, right? So it also remembers that. So and you can mix parameters, like this mix out model gives a recipe for this. Now let's move from domain specific pre-training to multilingual pre-training. So we talk about mainly pre-training on English data, but what about pre-training for other languages? So one thing can be, I can do monolingual pre-training of BERT on different languages. Like I can say, okay, I have a BERT for Dutch, I have a BERT for French, Vietnamese, and so on, right? I can have BERT for different languages. But what if I can pre-train a model on mixing multiple languages, right? I mean, so I can have a large mixture of languages and pre-train model on that. So MBERT, MBART, XLMR, MT5, Byte5, these are examples of models that have been pre-trained on large set of languages. And the good thing is that you can now do transfer across languages, because you are putting all the languages together and the languages have similarities, they are using similar words. You can do transfer of capabilities from one high resource to low resource and so on, right? So that's why this is typically a preferred approach, that you use multilingual pre-training. Now it started with BERT model itself. Like BERT has a multilingual variant called MBERT, and this is the same architecture as BERT, but the data set they used Wikipedia data set with 104 languages, and they have of course a slightly higher vocabulary, 110K word piece vocabulary, and same training objective that BERT used. Now they do something interesting while selecting the vocabulary. So for example, so what would happen in the data? So although you are saying 104 languages, some languages will have a lot of data, some language will have very small data. So let's say for an LF language, this is the probability of that language in the data, right? How much data you have for that language divided by all the data that you have for all the languages. And what may happen, so if you just use the probability as it is, so high resource language will have huge data and low resource language will have very small data, right? So there will be imbalance. So what they did, they said, okay, I can take this probability and do some temperature sampling. That is, okay, I'll sample if a language has lesser data, I'll sample that more than a language that has more data. So you can do different sampling. So if you do 1 by 5, so you get a curve like that. So where you are sampling the high resource a little less and low resource a little more. So you can vary the temperature so that you can sample different languages accordingly, right? So t equal to 100 is like roughly uniform sampling, right? So you are making like, it's like each probability to the power roughly 0, so you get equal value for all. So this is not desirable always. So you go for somewhere in between, right? You go for somewhere in between, right? So and the same BERT repository actually lists this particular MBERT model that one can use for multilingual applications. Now after MBERT, lot of efforts were done. I mean, on different directions. Like XLM was one of the very popular model that said, okay, because I am using multiple languages, I can use other kind of pre-training objectives. So they started talking about translation language modeling. So TLM objective. So what is the idea? So you are doing master language modeling, good. You're masking some words, but you will also have some parallel data across languages. So you also use parallel data. So what I will do, I'll take two sentences, one in say language English, another in French. So I'll put them one after another, and when I'm trying to unmask a token, I'll also make use of the parallel sentence, right? So I'll have the entire context. So I can also make use of the French sentence to predict an English mask and an English sentence to predict the French marks, right? So you can look at both the sentences to predict the mask token. So very similar to how we were learning the cross-lingual embedding, right? And we talked about that. So you can use the parallel sentence to create this translation language model objective. Now, so this was XLM. Now XLM-R is, I would say, one of the most popular encoder-only model that is available. So they scale the amount of training data a lot. So till now, people were using Wikipedia data, but they started using common crawl data, and that was, if you can see, this is like in log scale. So in GBeej, the size of common crawl is much larger than Wikipedia, right? And especially in the tail side, you have much more data for languages than you had in Wikipedia. So this gave a huge data, I mean, to pre-train the model, and that's why XLM-R became very popular. It gave huge performance improvements over say even BERT, large MBERT, and so on. Yeah. So across languages, you see average improvement over XLM version we talked about, MBERT we talked about, so was quite high. Right? Even for zero-shot classification, where models are fine-tuned on English data set and they are directly evaluated on other languages. So these were the encoder-based models. So you also had encoder-decoder-based models, multilingual. So MT5 was one such model. So we used MC4 dataset, so that had even better than the previous dataset we talked about, and they used also some temperature scaling, so that they can upsample the languages that have not been that are not so common in the data. Like this is the percentage of data if you use the original data set, but you can use different sampling to increase the proportion of data sets, right? So that's what they used. It will decrease the high resource proportion, but increase the low resource proportion. So they had 107 languages in their mix, and they used upsampling so that they can have a better representation of the low resource languages. And they found, so this is the MT5 model. So this is an encoder decoder model, and this had like variation from 300 million parameters to 13 billion parameters, 101 language on MC4. So I mean, this was like this is one of the best models in multilingual. If you want to do multilingual encoder decoder tasks, MT5 is one of the best models. So now how do they evaluate it? I mean, there are many tasks on which they evaluate. I'll just talk about one particular setting, right? To just give an idea like what does this cross-lingual transfer actually aims to do. So I'm talking about XLNI dataset that enables cross-lingual zero-shot learning. So what is happening here? So you have labeled training data for task X only in language A, right? So same task now you want to perform in another language B. So can you use this training data in task on language A? You fine-tune the model, but because it has multilingual capability, maybe it can also transfer to other languages, right? So from high resource you transfer to low resource. That's a very central idea of mixing languages, right? So you may have no label data for the same task in language B, but you may have unlabeled data for language B that you can use in pre-training that you already made use of, right? So like here, this is the English entailment task. So you have the premise and hypothesis. You have to predict the label, right? The same thing you have in French, Spanish, German, and other languages, right? So what they do, they say okay, they will see how much you can transfer from. So it's a zero shot transfer. You train it for English and see what is the performance in other language. So just zero shot in other languages, and you see this already performs a huge, very high performance, already gives a very high performance, right? Much better compared to say Ambert, so 65, and this is giving you 85 zero shot performance. So this was also true for other kind of tasks that we will talk at some point of time. Now they did some other experiments. What if we use some machine translation system to get more labeled data? So that is, I already have labeled data in English. What if I translate it to these languages and add it, right? So that you can do. So they tried it. So you can translate train. You can translate and train on that particular language. This boosts the performance, but this is not so much improvement compared to what you already got here, right? So it gives further improvement, but this was huge. So that was some very nice ideas from MT5 model. You can have models trained for language family, like for Indic language, as you have this Indic bird trained on all 22 Indian languages, and in the paper it has been shown to perform better than all these mbird and XLMR for Indic languages tasks, right? So this is the encoder model. You have Indic BART also, that is the encoder decoder kind of model. Now one thing though that comes when you are pre-training with multiple languages is the curse of multilinguality. So this was seen in this paper by Konu, that suppose I fix the size of the model. Now I am increasing the number of languages. So what will happen? The capacity per language will decrease, right? So this is like you are taking low resource language. So as you increase the number of languages, slightly you increase, but then you start decreasing the performance. Same thing happens for high resource language. So it's a decreasing trend as you increase the number of languages in the mix for a fixed size model. So that means if you have to increase more languages, you will also have to increase the capacity of your model, and you have to use larger and larger model so that you don't see a drop in the other languages. So now coming back to the vocabulary point again, see what happens. So different languages are not represented the same manner, right? So what happens, first you train your word piece or BP tokenizer once through all the data, and because it is based on frequency, if some data has some language has high representation, its token will get featured more, while other languages that do not have representation will just be featured as very small subwords. Like in an example, it's English sentence and the Hindi sentence, and you can see Hindi sentence, just a single word, single syllable is being treated as a single token, right? And this is what you can measure by fertility, that is number of tokens per word on an average. And if you are saying high fertility, remember decoder, you have to generate one token at a time. So you will have a lot of inefficiency during decoding, right? Because you will have to generate one token at a time, and the number of tokens are increasing a lot. Like GPT-4 model, the fertility for Hindi is 5.3 versus compared to other models like Bloom, it is just 1.38. So you would prefer to go to a model like Bloom for generating for Hindi rather than going for GPT-4 that has a high fertility. So what happens? So what do you do if you know that your language is underrepresented? So how do you put the vocabulary? Now remember, we can train from scratch for that language, but that's not the solution, right? You can train from scratch, but can you extend the previous model to include the vocabulary of your language? So that is also people have tried. You can extend the vocabulary. So what you can do, so let's say this is your language data. You take the data and you train tokenizer on that language, and you have a new vocabulary that you want to include, right? So you have a new vocabulary. Now you already have an existing vocabulary from your pre-trained model. So what you can do, you can say, okay, I want a combination of these two. I concatenate the vocabulary, new vocab to the existing vocab, and I get an extended vocabulary. But in the embedding matrix, I do not have anything for the new vocabulary. So I have to initialize this with some random embeddings, and I have to learn the embeddings for this. And for that, I have to start from this base LLM and further pre-train it so that I learn the embeddings for this new vocabulary, right? So I have an LLM with extended vocabulary, but I do not know the good embeddings for these tokens. So what I will do, so I'll take this base LLM that has been already pre-trained, but also some monolingual data in my new language, and I do continual pre-training. Remember, with the extended vocabulary, right? And this is my continually pre-trained language model. So this is another way, like a mix where you can extend the vocabulary first and then continue pre-training, right? But you have to do a lot of engineering hacks. For example, we talked about continual pre-training. You may forget your previous knowledge. So you want to retain your English competence. So you should include English also when you are pre-training. So some proportion of English, right? And you may pre-train on parallel data. You can pre-train using Romanized data. So you may have to do many different kind of tricks. So this is typically what people do to extend to vocabulary. Right? Of course, this is a good research field, and a lot of research has been happening. Right? Now, I'll end this lecture with the related concept of uptraining that I had introduced in the last week. So remember, we were saying that we have some efficient concept like group query attention or multi-query attention that I want to make use of, right? But see, the problem is that I already may have some pre-trained language model like T5 that has been pre-trained with multi-head attention. Now, group query attention said, okay, I'll have one single key and value for the entire group, but that's not how T5 is trained. So if I do something like I can do some polling to take all this W, so let's say WK for head 1, WK to head 4. Let's say I'm putting a group of 4 heads. I can pool them and I'll say WK for this group 1, right? This is the key projection matrix I can create. But it was not trained to make prediction using that, right? So it was trained to make prediction using individually. So I have to do some pre-training of this T5 model so that it starts working with this pooled representation, right? And that's what is called uptraining. So it's like continual pre-training with a different representation, different architecture, you can say. So I start from these checkpoints. Now I can do pooling, right, to get this groups, and then do some small amount, say some alpha proportion of original data. I can continue pre-training so that it's now used to making use of these groups rather than the multi-head attention, and that's what is called uptraining. Okay. So what I can do in uptraining, so when I decided, I take the checkpoints, I have this projection matrix, right, and for the group I do a mean pooling, right. This is like you can do it for multi-query attention, multi-group attention, and now once you have done this pooling, now you start from that and continue your model. You pre-train your model, but now it will work with the pooled representation, right. So it learns now how to make use of this to make its next token prediction or whatever pre-training task, and then it is at inference time also it can work with this efficient representation. So that's very important. So you cannot just directly start using those if they are pre-trained model, because that may not work directly, but with uptraining it may. So even with MOE architecture we talked about, so one can say, okay, this is a good architecture, but what if how do I make use of an existing model, pre-trained model that does not use MOE? So what we can do, like this particular paper showed, that you can take the original architecture and just copy it into an MOE architecture. So what you can do, you can have E different copies of MLP, right? So you can have E different experts, and this router is what something you initialize. This is a small number of weights. You initialize this router weights and initialize like that, and you do uptraining. You do uptraining on the new data, right? So what will happen now? All the parameters are already initialized. You don't have to do from scratch. You only have to learn this router, right? So that, and it can pass it to one of the experts, right? So this is like one of the, and you have to like continue updating these parameters so the different experts learn to vary in their own way, right? So this is like another interesting thing from pre-training called uptraining. So yeah, I mean, for this particular lecture you can use various reference papers that we have given in the slides. So that will be one of the best ways to learn more about it, and that also ends our week 6. Thank you all.